Hi, my name is Shahnawaz. In this lecture, we'll talk about projective varieties. So, if we consider the complex plane with strong topology, then we see that the affine n space an and the affine varieties, except possibly for the pointers. So, these uh, varieties they are not compact, but compact spaces are much nicer than the non-compact ones. So we want in some sense to compactify affine varieties. Now this is done by adding points at infinity and looking at a projective space and projective varieties, which are nothing but the zero sets of the homogeneous polynomials on projective space. Now these projective varieties are now compact with respect to uh, I mean with respect to the strong topology. Now we begin this lecture by defining the projective space. So we have this definition. So let us define a relation. So define a relation. Let us denote this relation by tilde on the points of the non-zero points of n plus one dimensional space. So this zero is the zero vector in this space by, so we say a point, say a naught through an, which is an n tuple, n plus one tuple. So we say this is related to b naught through bn, if and only if there exists a non-zero scalar. I mean, if and only if there exists, say lambda in k plus one, k minus zero, such that this point a naught through an, this is the scalar multiple of, the point b. I mean, these 2 points differ by this scalar multiple. So, so one can note that this relation is an equivalence relation. So then this tilde is an equivalence relation. So one should verify this. This is trivial. Now the equivalence class of some point. So the equivalence class uh, of some point, say a naught through an in the set k n plus 1 minus 0. So this is denoted by, so this is denoted by, the point with square bracket is a naught through an. Now the quotient, see the quotient set, the quotient Pn, which we sometimes write as Pnk, but as a shorthand we write Pn. So this is the set Kn plus 1 minus the point 0 mod out by this uh, relation. We identify all in the bottom. So it is the set of all, the equivalence classes, such that this point a naught through an, this is a non-zero n plus 1 tuple. So this set, I mean this Pn, this is called the projective n space. So this is called the projective n space. So the AIs are called homogeneous coordinates. So the AIs are called homogeneous coordinates. So these are called the homogeneous coordinates of the point P, which is the point A naught through AN in Pn. So an element in the projective space Pn is just a vector in Kn plus 1 after multiplying by a non-zero constant, which is equivalent to saying it is a line, I mean a one-dimensional subspace of Kn plus 1. So such a line is determined by a non-zero vector on the line. So for example, let us look at the real projective line. So this is a real projective line. So or we denote it by P1R. So what do we do? So as mentioned uh, above, so we'll make the set P1R that consists of the collection of lines in R2 through the origin. So what do we do? So we define uh, a relation tilde on the set R2 minus the zero vector by, so we say the point x1 y1 is related to x2 y2 if and only if there exists a non-zero scalar, I mean a non-zero real number, such that this x1 y1 is the lemma times x2 lemma times y2. So then this projective real line, I mean the projective space on R is just the set R, sorry, R 2 minus the point 0 mod out by this uh, relation. So we identify uh, I mean all such points. Now why this is called the real projective line? So the line is actually the equivalence class. So if we look at this system over here, so sorry, so this is R2. So if I look at this line over here, suppose this is point say 1 1, then this point over here, this will be suppose 2 2, because these two points they differ by I mean scalar multiple. So this line will be a point in the projective space, because this line is just an equivalence class. Now if I look at this line, this will be, I mean, this will be some different equivalence class, and the set of all equivalence classes is just the collection of these lines through origin. So P1R is actually the collection of all lines through the origin. Now this line, this line over here, this looks like R but with a point at infinity. So for example, so uh, if x is not equal to 0, then we can write xy as we can write xy as uh, 1 times y by x by taking lambda to be equal to 1 by x. So by taking lambda to be equal to 1 by x, so that means every point on this line, so almost every point, almost every point looks like the point 1 comma a. So we can put this expression over here to be equal to a. So every point on this line looks like 1 comma a for some a in R. So that means uh, for each a in R, we have a point 1a in the line over here. But when x is 0, so but when x is equal to 0, then there is an extra point at infinity. So then there is an extra point at infinity. Uh, I mean, this point will look like 0 comma b, which is same as 0 comma 1, because we can multiply by 1 over b. So one can note over here these 2 points, the points, the point xy here, both x1 and y1 cannot be equal to 0, because we have the set r2 minus 0. So if if the first entry over here is 0, so b cannot be equal to 0, so we can multiply by 1 over b. So this equivalence class is, this is, these 2 points are same, so this will be the point at infinity. Now let us look at the relation between the projective n space and the affine n space. So we have one more definition here. So for I equal to 0, 1 up to n, let ui be the set of all those points in Pn such that the ith coordinate over here is non-zero. So this is non-zero. Now we can define a map. So now define a map, say phi I from the set ui to the affine n space by, so this phi I, this takes a point here let us call this point, say, a naught through an. So it maps this point to the point a naught by a1, sorry, ai, a1 by ai, so on, ai by ai, which is same as 1, so on, an by ai. And let us, so this is I mean a vector with n plus 1 entries. So we draw a hat here to mean that this component is not there. I mean this entry is omitted. So where, and the hat means the component is omitted. So the map phi I is obviously a bijection. First, it is well defined. So the map phi I is uh, obviously a bijection. With the inverse. So to prove it is a bijection, I mean to see it's a bijection, we have to exhibit its inverse. So with the inverse psi I from an to ui, given as, so this psi I, this takes a point in the affine n space. Let us call this point by, I mean the point b naught through b I cap. So this is not there, this component. So through bn. So this is just an n tuple. So it maps this point to the point b naught. Sorry, I had to draw a square bracket here. So b naught to, so at the ith component I will write 1 through bn. So this is a point in bn. So one can note that if we compose these two maps, we get the identities on their respective sets. So note that uh, if we compose psi I with phi I, so this will be a map from ui to ui. So it is given as, so psi I of phi I. So when we operate phi I on the point, say a naught to an, we get psi of I of the point a naught by a1, sorry, ai through ai by ai. So it is cap there, I mean through an by ai. So this is same as we get back our point a naught by ai through, so here this is one cap, so this will be one here, so on an by ai. But this is same as, this point is same as, because ai is non-zero, so we can multiply by ai to get back the point a naught ai here and an. And if we do otherwise, I mean phi I composed with psi I, so one can note over here this psi I of phi I, this behaves as the identity map. So one can wrote here, I mean one can write here. So we have psi I composed phi I is actually identity map on ui, and phi I composite psi I, which is a map from I mean um, from an to an. So this is given as, so phi I of psi I of, let us take a point here, so b naught through bi cap through bn. So this will give us phi I of b naught through 1, I mean 1 over here through bn. So this bi cap is not there, so instead of bi cap we write 1 here, and so this phi I, this will give us a point b naught through 1 cap through bn. So 1 cap is not there, so this point over here and this point over here, they are same, and hence phi I composite psi I, this is actually the identity map on the affine n space. So one can remark this over here. So we call a j by ai the affine coordinates, the affine coordinates. So when defining this map over here, so when we define this map over here, we call these aj by ai's the affine coordinates of this point a naught through an. So we call these the affine coordinates of the point P, which is a naught through an with respect to ui, with respect to ui. So in particular, we want to use size 0 to view Pn as an. So I mean, so in particular, uh, we want we want to use size 0 to view the projective n space as an, with some uh, with some uh, added points at infinity. So actually we identify an with u0 by identifying, so we identify uh, an and u0 by identifying by identifying the n tuple a1 through an, which is in the affine n space, with the point 1 a1 through an, which is in the set u0. So thus an can be think of as a subset of pn. So thus an can be think of as a subset of pn. uh, so thus for any subset, so therefore for any subset, say X, of the projective space Pn, we have, so if we look at this intersection X intersection with An, so this is actually the image of the set under the map phi 0. So in particular, so this Pn is actually the affine n space with some points at infinity. Let us call that set to be h infinity. So this h infinity contains the points at infinity, where h infinity are those pointers in the affine space such that whose first coordinate is 0. I mean a naught is 0. So h infinity here, this is called the hyperplane at infinity. So h infinity is called the hyperplane at infinity. So in case n is equal to 1, so we write this infinity as to be the point 0, 1 in P1, as we saw over here. So we looked at this point over here. So this is our infinity. So this is the point at infinity, which is the extra point. So or we can say the affine 1 space is actually, sorry, the affine, so the projective 1 space is actually the affine 1 space union this point, which is the point infinity. Now we want to define projective algebraic sets in Pn as zero sets of polynomials in the polynomial ring in n plus 1 variables. So there is, however, a problem. So unlike the affine case, a polynomial g in the polynomial ring in n plus 1 variables does not define a function on Pn, because so in general, if we take the point G A naught through A n, this is not going to be equal the G lambda A naught through lambda A n for some lambda not equal to 0. For instance, so if we look at the polynomial f in the polynomial ring, two variables, say x0, x1, such that f is actually equal x1 square minus x naught, we have then, so we have, if we look at the polynomial f evaluated at the point 1 1, we get 0. But if we look at the polynomial evaluated at some scalar multiple of this point, say minus 1 minus 1, so this is not equal to 0. So this problem is not there if f is homogeneous. Now what do we mean by homogeneous? So we have a remark here. So if we take a point, say G, in uh, the polynomial ring in n plus 1 variables, so this is homogeneous. So this is homogeneous of say degree d. Then for all lambda in the field K, g of lambda, say a0 through lambda an. So this is equal to lambda to the power d g of a0 through an. So thus the question whether g of a naught through an is 0 depends only on the point a naught through a1 in the projective space. So thus the question whether uh, g of a naught through an is equal to 0 depends only on the point. So this is trivial to verify. Trivial to verify. So now we have this definition. So we have the definition. So let us consider G to be a polynomial in n plus 1 variables. So this is a homogeneous polynomial. So by homogeneous we mean this situation over here. I mean if this thing is true. So this is homogeneous of degree d. So this is homogeneous polynomial of degree, say d greater than 0. So one also says G is a form of degree d. So one also says that G is a form um, of degree d. So a point, say P equal a naught through an in the projective n space. So this is 0. So this is a 0 of G, and we write G of P is 0 if and only if I mean G of a naught through an is equal to 0. This is independent of the representative because the polynomials are given to be homogeneous. So this is independent of the representatives. I mean a naught through an. Let us draw the curved brackets. So if we consider, now let us consider S to be a subset of the polynomial ring. Uh, so so to be a set of homogeneous polynomials. So the projective zero set of S. So the projective zero set of S. So this is defined as, so we call this as Z of S to be equal to all those points in the projective n space such that f of p is equal to 0 for all f in the set S. So this is called the projective zero set. So a subset of the form, a subset, a subset that is called uh, a subset, say a of p to the power n of the form. So if a is of the form z of s, so this is called the projective algebraic set. Is called a projective algebraic set. So if S contains, say, finitely many polynomials, say f1 through fr, then we write z of f1 through fr instead of the set z of s. So if f is a form of degree d, then z of f is called the hypersurface defined by f. So if f is a form, so is a homogeneous polynomial of degree d. So if f is a form of, say, degree d, which is bigger than 0, then it is zero set. So then it is zero set in the projective n space is called the hypersurface defined by f. But if you remember, we have reserved this notation for the affine algebraic sets. Now to differentiate these two situations, we fix a notation to save ourselves of getting confused. So to distinguish between the projective zero set sets and the affine algebraic sets, and affine zero sets, we write, so zero set of a set of polynomials. So we write zp of s for projective zero set and za of s for the affine zero set. So the main reason for introducing these projective space is actually the Bezos theorem. Now, what is Bezos theorem? That is what we are going to study in the upcoming lectures. For example, in affine spaces, results on intersections always contain a certain number of special cases due to uh, due to asymptotes or um, I mean, due to asymptotes or some lines which are not intersecting. Uh, in the plane, two distinct lines meet at a unique point, except when they are uh, parallel. But in projective spaces, these there are no such exceptions. So that is why we need these projective spaces. So in next lecture, we will give some examples of these projective zero sets.